here, drop there, and back up. Right? And then obviously this direction, you might see it at a different range. But by finding the intersection of those rays, you know them. If you assume straight ray path, you know the ray. So all you have to do is find the intersection of those anomalous amplitudes. And that basically tells you where your anomaly is. This is a very, very simplistic way of doing it, simply with orthogonal ray path. But we could basically take these sources along here and project them into these receivers over here and do something similar. So these are the geometry we laid out. You don't have to have it perfectly be a square, but you have to be able to at least correct the data for travel time or for attenuation. You can't use path lengths that are completely different from each other. So here's a known void distribution. Okay, the void is down there. So this square actually only hits the void in this little area. What I want to do before I look at the data is I want to show you what really happens to a surface wave when it hits a void. It's actually a fairly complex process. So again, what we have here is we have lateral distance from a shot. Obviously the shot's going to be over there. And this is a computer simulation. So we embedded a void in our subsurface model. We're doing forward modeling, and we're basically doing a full solution to the wave equation when we do this model. So we have a wave a surface wave that transmits from the source all the way down to the void location. What happens after the void location? Well, the transmitted surface wave is actually decreased in amplitude, as we expect. As you pass through that void, the amplitude drops. Notice also that the travel time even drops a little bit. You can kind of see the wave right here. It's complicated, but the travel time looks like it drops. If it were constant, it wouldn't quite be there. The big thing that you see is kind of an interesting thing. You see a wave coming this way. So we know that this travel time is increasing as it goes away from the void location. So that's a wave. We saw an example of that last time in that diagram. So what's that? That's a wave that hits a void as a surface wave and bounces back the other way. It's really kind of a reflection off the void. It's a surface wave reflection hitting the void and coming backwards. So the intersection of the backscatterer to the forward kind of tells you where the void is. Right? They have to be the same travel time at that point. The other interesting thing that we noticed is that right at the void, there's actually appears to be a wave train that extends for a long period of time. And we believe this thing is basically the surface wave that hits the void area, it backscatters, it transmits through really weakly, but it also scatters up and down here and creates kind of a resonant column right above the void. So what we found is that there are probably 3 different techniques that we can use to image the void. If we have a receiver directly over the void, we can probably, or receivers everywhere, we can probably use this resonance technique. We can use the backscattering technique. That's really more like a conventional seismic. And we can also use the transmitted wave. The transmitted wave is by far the easiest because typically it's the largest thing that we see. Okay, so So what this shows you is the change in amplitude, the peak amplitude of the wave after it's been transmitted through the void. So what this shows is at different depths to the top of the void, how does the amplitude of the wave change? And what you can see is that the bigger the void, the bigger the amplitude change. Okay? The more extensive the void, the bigger the block is. So that kind of makes sense. What else happens? Well, the shallower the void, the more likely it is to see the amplitude. Why is that? Because surface waves are basically more sensitive to shallow media than they are to deep media. Why do we actually, so this is the, basically this would be the zone where we would be able to see the void with transmission imaging. And you can see that at a 1 meter void, it's pretty darn hard to see. What happens as we go in here? We believe this is related to constructive interference, that the surface wave is actually not penetrating through the void, it's bouncing off of it and increasing the amplitude in the void is moving. So we can use these forward models, again, to match to our real data. Just like we were talking about with the surface wave analysis and looking at velocity. We're basically, just like you were doing in gravity, just like you're doing on your homework now, we're building hypothetical models, and we're seeing what the response is, data response, from the computer. Then we're comparing the computerized data response to our real data. And this is called iterative forward modeling, but it's basically taking the data and finding a model that fits the data. So let's look at some real data. These are all models. Let's look at some real data. Okay, here is an example of the survey, and the geometry kind of looks like this. You've got a square, and you've got your southeast corner right here, and you've got your northeast corner right here. And then you've got your northwest corner right here, and your southwest corner right here. And we're essentially looking for travel times from a constant offset. So we're sending waves through this way, different receivers there, and we're sending waves through this way. Okay? So if you're tracking the southeast corner, which would be right here, the source would be here, the receiver would be there. If you're looking at the northeast corner, the source would be here, the receiver would be there. If you're looking at the northwest corner, the source would be here, the receiver would be here. And if you're looking at the southwest corner, the source would be here, and the receiver would be here. Or you might be looking the other direction, clockwise versus counterclockwise. So what do you see? Well, it's pretty cool. In the southwest area, you see that the amplitude and the travel times decrease in this area here. And then the travel times increase and actually dip in this area and then come back up and are relatively constant until they hit this area right here. And notice what we see right in here. We see an increase in the travel time, and we see what looks like that resonance phenomenon, staying there. it would appear, just from this data, that there may be a void somewhere in this area. So now the goal of the imaging is to take all the data, not just this subset, and generate a tomographic image in the computer of what the amplitude and what the, basically what the travel time or velocity does and what the amplitude does. So here is the attenuation tomography results for this particular location. And what you can see is that there is an anomaly down in this area. And the amplitude actually increases and is largest up in this area and kind of transitions between here. Well, if you'll recall, and here's the travel time anomaly. There are kind of a few edge effects, but the velocities get higher and the travel times gets lower in this area, and they actually grade into much lower velocities as you go in this direction.